All right, so this is example number 4, and something a little bit different is going to happen in this example. And I apologize for how low tech this is. Sort of a last minute plan to do these video notes. So we're going to treat this just like we did with the last example, where we pick 2 equations, eliminate a variable, pick a different combination of 2 equations, and eliminate the same variable. So we have 2 systems of 2 because we know how to solve those. So I'm going to start with these 2 here because why not? So there's nothing I can simplify all of these equations by uniformly. So let me just label them first. Okay. So I'm going to start with equations 1 and 2. And let's go ahead and eliminate the y's because I'm just looking here and I see a 1, a 5, a 1. So we can multiply this all by -5, this all by -5, and eliminate both with this. Or we can eliminate these 2 just by keeping this one a positive y and making this one a negative y, and go from there. Okay, I'll just start. So let's take 1 and 3 first. So I'm going to keep 1 as is, and I'm going to change all the signs on number 3. So basically I'm multiplying everything by -1, so I'm not changing the value of the overall equation. It's still true. And I eliminate my y terms. So now I have -3x plus 4z equals 8. Okay. Now, let me see if I can get a little less shadow on this guy here. Now what I'm going to do is I'm going to choose equations 1 and 2. 2 I'm going to keep as is. And 1 I'm going to multiply everything by a -5. So I have -5x minus 5y minus 5z equals -10. Okay, so what's going to happen here is a little bit funky. If I look at the ratio of the coefficients here, 1 to 1 to 1, 5 to 5 to 5, these could all reduce by 5, but that doesn't carry over to the 2 and the 3. So I'm about to discover what that means when I try to eliminate. So here, not only did my y's eliminate, but so did my x's and so did my z's. So if I look at the sum of what remains on the left side of the equation, it's a 0. And -10 plus 3 is -7. Now the problem is that's not a true statement, ever. So even though I was able to eliminate these 2, because I'm looking at a system of 3, and because these 2 are not compatible, that kind of ruins the whole system. So when this happens, we say that there is no solution, because there's no combination of x, y, z that has a sum of 2 such that when I take each of these separately, multiply them by 5, I have a sum of 3. And then, so these 2 are not compatible. Whether or not this could be compatible with this one or this one becomes irrelevant because there's no scenario where all 3 work together. So just like in the last example, you can sort of look ahead of these and think, okay, well, this x plus y plus z equals 1 is really nice and simple, but what's more interesting is this equation as compared to this equation. You might notice that, oh, 6 times 2 is 12, and 9 times 2 is 18, and 12 times 2 is 24, and all of my signs match up. So basically, if I double this, I should get this. However, if I double 14, I don't get -11. So that's going to cause a problem. So in order to sort of see what that means, I'm going to choose to try to eliminate anything from 2 and 3. So let's say we want to eliminate the x, or we attempt to eliminate the x from 2 and 3. What I'll probably choose to do is multiply everything here by a -2. And then I keep my third equation as is. So now when I eliminate, my x terms are gone, my y terms are gone, my z terms are gone, and I'm left with 0 remaining on the left side of the equation. When I add up these columns here, I have a -29. really doesn't matter what this is as long as it's not 0. Because, well, if 0 equals 0, that's a different scenario, right? But 0 equals negative 29, that's false. So again, I really don't need to take this anywhere else because these two equations are not compatible. So there's no solution. There's no possible combination of x, y, and z such that when I multiply these coefficients, I get a sum of 14 that also, where it would also be possible that I could multiply those coefficients, those variables by these coefficients and get a sum of negative 11. Whatever this says, this is basically the same relationship, but all of my coefficients are doubled. So for these two to be compatible, this would have to be a 28. But the problem is then they'd actually be the same equation, so I wouldn't have a system of 3 anymore. So at this point, these guys are probably all starting to look a little bit familiar, and that's okay. There are really only so many coefficients we want to give students. We attempt to not give you anything too horrifying for a coefficient because it gets messy when you multiply. That first example being the exception, of course. So again, I'm not sure what's going to happen here. These guys look similar but not the same. So let's see what happens when we try to eliminate something from equations 1, 2, and 3. I'm thinking maybe the z's, because why not? They'll eliminate right away. That way I don't have to multiply through by any coefficients. So if I keep these guys as is, and I eliminate the z's, I have 2x minus 2y equals negative 6. Okay. So not much I can do with that. I could divide everything by 2 if I wanted and say x minus y equals negative 3. Okay. But that doesn't really do anything for me yet. I need to see what happens when I try to eliminate again. So because this was a positive x and a negative x, I'm going to eliminate from 2 and 3 because, positive z and negative z. I'm going to eliminate from 2 and 3 because my z's will just kind of magically disappear again, which is convenient. So I'm going to set this up again with equations 2 and 3. I have x minus y minus z is negative 3. And I have 5x minus 5y plus z is negative 15. So again, the z's cancel, and I have 6x minus 6y equals negative 18. And again, I can reduce this guy, right? So if I do that, I'm going to end up with, I can reduce by 6. X minus y equals negative 3. Okay. So now the two equations of 2 that I ended up with are identical to each other. This is a little problematic because I need to have two unique relationships to solve a system, and right now I have the same relationship. So you might not see it at this stage, but let's say we just went ahead and we eliminated. We multiply everything here by a negative 1, so that changes all of our signs. And so we eliminate and we get x is gone, y is gone, so only a 0 remains, and negative 3 plus 3 is also 0. Now this is true. It's always true. So what that means is that if I look at the relationship between these equations, it boils down into a relationship that is shared by the relationship between these two equations. It's a little tricky to make sense out of, but it's sort of like saying, in order to solve a system of 3, I need to have 3 unique relationships comparing x, y, and z. I don't here. I only have 2 relationships that are unique comparing x, y, and z. So that's not really going to help me. And if I look a little more closely, I'll see that these two equations are actually the same. This one just has been multiplied through with a coefficient of 5. So having 2 equations is not enough to get a unique solution for a system of 3. So that means that it doesn't mean that x, y, and z can be all real numbers. What it means is that some combination of x, y, and z will work for these two and this one, and it's not unique, so there might be multiple combinations, and there are multiple combinations that will work. So what I say here is not that there's no solution, but there's many solutions. And specifically how many? Well, we can say there's an infinite number of solutions. Okay, it doesn't mean all solutions. It just means that there is more than one unique solution. So if you're sort of paying attention here and you see all these even coefficients, that's handy. We can start like simplifying this stuff out and seeing if we have a repeat relationship with like we did in the last example. So here I can take my first equation and simplify this down to be x minus y plus z is 6, right? So I've divided every coefficient in the constant by 2. This guy is 5x minus y plus 5z is, what's that, 30, okay? And this guy is x plus y plus z is 6. So at first glance you might go, wait a minute, these two are the same, but they're actually not, right? Here we have x minus y, here we have x plus y. Here when we divided everything by 2, we had a 5, a 1, a 5, and a 30. So far I'm not seeing any repeats here. So let's see what happens when we try to eliminate. So I'm going to pick the first and the third to eliminate. I should have bumped this guy a little to the left. So I have x minus y plus z is 6, and I have x plus y plus z is 6. So here what I have is 2x plus, these guys are gone, 2z is 12, okay, which says x plus z is 6. Okay, so that's one of my systems of 2. Now I tried 1 and 3. Why don't I redo this with 2 and 3? Okay. So if I redo this with 2 and 3, I'm going to have 5x minus y plus 5z is 30, and x plus y plus z is 6. Again, my y's disappear. I have 6x plus 6z equals 36. If I divide everything here by 6, I get x plus z is 6. And again, these guys match. So if I look at the original, I'm not necessarily seeing that 2 of these are identical to each other, but what happens is that when I eliminate here, I get 2 identical equations. And again, if I'm not sort of picking up on the fact that these are identical, and I just go ahead and try to eliminate by multiplying everything here by a -1, I end up with 0 equals 0, which is always true. So what that means is I essentially can boil this down to a system of 2, and the system of 2 is identical. So it's not really a unique system. So again, I have many solutions, or I have an infinite number of solutions. Essentially, those mean the same thing. Before I move on to the last couple examples that are word problems, something felt a little funny to me at that last example, so I wanted to hop back to not practice 5, but example 5. So not the one we just did, but the one before. I think I made a comment that these two were the same. They're really not. I'm looking at these coefficients again. 1 times 5 is 5, 1 times 5 is 5, 1 times 1, I'm sorry, let me try it again. 1 times 1 is 5,